Hey there, and welcome to 3.7 on quadratic inequalities. Today we've got two objectives looking at being able to graph and solve quadratic inequalities, graphing them in two variables and solving them in one variable problems. And so you'll see that our two standards do relate to both those, so create and solve linear equations and inequalities in one variable. And then we're going to use systems of equations and inequalities to represent constraints arising in real world situations. And so that's what we're going to look at when we get down to the last example today. And so just a reminder on how to graph, right, with inequalities. Remember that you need to graph the related function first. And this is true for linear equations, quadratics, exponentials. Doesn't matter what type of function we're dealing with. You graph the related function first. And so remember, if the line will be solid if we're equal to, so remember if we're like greater than or equal to or less than or equal to, and it will be dashed if it's not equal to, so just less than or greater than. Our second step is to test a point that is not on the parabola. So if I've got my parabola drawn, I'm not testing a point that's somewhere along the parabola. I'm testing a point that is either inside the parabola or outside the parabola. We'll talk about that in a second. And two really good test points are the origin or 0, 1, because you'll never have both in a function. And so plugging in 0, 0 is really nice because every time you plug in 0 to a variable, anything multiplied to it, 0. And anything added to it is itself. And 0, 1 is really nice because that just puts a 1 for y, and it again makes a really great test point. And then shade accordingly. So again, if we find that this point here works, then we're going to shade in here, right? But if that point doesn't work, and we test this other point that's out here, then that would be where our shading is on the outside of the parabola. And so again, we'll test those out as we look at a few of these problems today. And so looking at example 1, we want to graph y is greater than x squared plus 2x plus 3. Now remember, we could use a couple different methods here to graph this up. And so we'll go to the axis of symmetry. Remember, that's x equals the opposite of b over 2a. If you've been struggling with graphing quadratics, today's a great day to relearn. So the opposite of 2 over 2 times 1, that's going to give me negative 2 over 2, which is negative 1. So my axis of symmetry is coming down here at negative 1, x equals negative 1. And remember, we're going to plug that back in to find our vertex. And so we're going to get y, we're going to equal to for the moment so we can find the vertex. Plugging in the negative 1 squared plus 2 times the negative 1 plus 3. So y is equal to 1 minus 2 plus 3, so y is equal to 4 minus 2, so y is equal to 2, which means my vertex is at negative 1, 2, right here. Okay. Next thing I notice is that my y-intercept has to be 3 because I'm in standard form, and we'll reflect that point across, 1 unit right, so 1 unit left. And then I could plug in positive 1 to get me one more point, and so plugging in y equals to 1 squared plus 2 times 1 plus 3. And so we get 1 plus 2 plus 3, which is 6. And so from plugging in 1, we get 6 over here. And I'm 2 units away, so I'm going to be 2 units away this way at negative 3, 6. And so this gives me my parabola here. We can see that U-shape starting to take effect. Now, what type of line, come back up to the top here, right? Graph the related function, and remember, the line will be solid if it's equal to, dashed if it's not equal to. Well, I'm dealing with greater than here, and so my line will be dashed, and so I'm going to make this a dashed parabola. Okay? And so now we get the testing points. And again, I told you that 0, 0, 0, 1 would be really great points to choose because, again, plugging in 0 and 0 would give me a really easy inequality to solve. And so I get 0 is greater than 0 squared plus 2 times 0 plus 3. Well, that's 0 and that's 0, so we get 0 is greater than 3, and that is a false statement. And so this point does not work. And so where's my shading going to be? It is going to be inside. And again, I could go and test a point and see that it will work. So for example, if I test like 0, 6, 6 will be greater than 3 because, again, those cancel out. So 6 greater than 3, that does work. So my shading would be inside the parabola in this case. Now, I don't want you to get fixed up on things being greater than or less than being inside or outside, because depending on the opening direction of my parabola could change if I'm going to be inside or outside. An easy way to think about this, though, is this. This says that y has to be greater than the related function, right? And so if I go to my y-intercept, where is y greater than this parabola? Well, it'd be above my curve, right? And so being above the curve on the y-axis puts me inside the parabola in this case. Okay, so again, make sure you're paying attention not to inside or outside, but again, think about y is what? Greater than, or y is less than. Okay, so let's look at example B here. We're going to graph this one up, and so again, we'll find our axis of symmetry first. Now, again, we could go to other methods, right? We could factor this. If you want to factor this, we go to negative 12, because that's a times c, and then we got positive 1 for here. So what are two numbers that are going to multiply to negative 12, but add the positive 1? Well, if we do our whole list, we're going to see that we're going to get positive 4 and negative 3. And so I get negative 2x squared plus 4x minus the 3x plus the 6. I can factor out a negative 2 from both of these, and so I'm left with, and also an x, so x minus 2. Factor in a negative 3 from both of these, I get x minus 2 as well. And now, pay attention to what happens here. I'm going to get x minus 2, I'm going to get negative 2x minus 3. These both have a negative, so the negative can come out front. And so I get this. Now, this is our intercept form, right? And so my intercept's going to be at positive 2, and this other one's going to be at, remember, it's going to be setting this equal to 0. Opposite of this, so negative 3 divided by 2, so that's negative 3 halves, which is negative 1.5. Now, does that give us a really great thing to go off of? No, but it kind of starts to give us an idea where this picture is, right? And again, that's one way to get those intercepts as well. The axis of symmetry, again, we could do the axis of symmetry from our original. X equals the opposite of b over 2a. So the opposite of 1 over 2 times negative 2 is going to give us negative 1 over negative 4, which is positive 1/4. And so my axis of symmetry is just here to the right of the y-axis. Okay, and so now I can plug that back in. So y equals negative 2 times the 1/4 squared plus the 1/4 plus the 6. And so y is going to be equal to negative 2. This is 1/16 plus a 4th plus 6. So y is equal to negative 1/8, because if I have two 1/16ths, that's 1/8, plus 1/4 plus 6. Common denominator would be 8 here. So I'm going to get 2 8s. And how many 8s would be 6 wholes? That's 48 8s. And so we end up 2 plus 48 is 49, and minus 1, or sorry, 2 plus 48 is 50. Minus 1 gives us 49 8s. And again, that would be 6 and 1/8. So I'm sitting right here, just above 6. And if we go back, we see that our y-intercept is at positive 6. So that point's going to be right here. And reflecting that across, that's going to be right here. And so we have 5 points there. Again, we could plug in like negative 1 and get a value and reflect it across as well. But we do have 5 points. This is equal to, so this will be a solid curve, like so. And then we need to test, are we going to be inside or out? So again, 0, 0 is nicely inside our parabola here. So if I plug in 0 here and 0 here, I get that 0 is less than or equal to 6. Is that true or false? 0 is less than 6, so that is the correct place for my shading. And so my shading will be inside this parabola in this case. And remember that anything inside this parabola would be a potential solution. And again, it would be really good if we continue these lines all the way down to the end of the graph so we can see what are possible solutions. Okay, so that's what we're looking at. Again, it's not complicated, and we got some different methods to get there to get our different points. Again, I used factoring this problem to get the intercepts because I knew the intercepts weren't going to be great. One of them's okay at negative 2, or sorry, positive 2. The other one, is at negative 3 halves. So again, just using the tools that we have to be able to graph these inequalities. Okay. And so now we're going to look at solving one variable inequality. So first things we looked at were graphing two variable inequalities into the coordinate plane. Now we're only dealing with a one variable problem, which means we go back to dealing with problems that are on a number line, not on a coordinate plane that require two variables, right? Because this is x, this is y. When we think about the number line is just x, right? And we've got 0 in the middle, negatives over here, positives over here, right? And so when we graph and solve x squared plus 5x minus 6 is less than 0, we could go to the quadratic plane and, call this y. And we could graph it up that way. And, we could. So y-intercept would be -6. Our axis symmetry would put us at x equals the opposite of b over 2a. And so it's going to be opposite of 5 over 2 times 1. So that's -5/2. And so my axis symmetry is coming through at -2.5. I could plug that back in. And so, again, you could use the decimal or the fraction, either case. So -2.5 squared plus 5 times 2.5 minus the 6 would be equal to the y. And so -2.5 squared, 25 squared is 625, so this is going to be positive 6.25. And again, it's a negative there. And so this would be minus 12.5 minus the 6. And so this would be -6.25 minus another 6. It's going to give us -12.25. So that takes us actually off the bottom of our graph here, down about here. Reflecting this point across, we're going to be 2.5 units to the right, so it ends us up at -5. That's -5 there. And we could put in one more point. We can go to like -2 or -1 and plot those as well. And so doing that, we're going to get -1 squared plus 5 times the -1 minus the 6. That's equal to y. And so we're going to get 1 minus 5 minus 6. And so 1 minus 5 would give us -4, and that gives us -10. And so I'm sitting here and here because I'm 1.5 units to the right, so I'm 1.5 units to the left. My shading here, my line would be not solid because it's not equal to. And so we can draw that as well. But here's the thing, is all these points are nice, but I need to know where it crosses the x-axis. And so if we were to factor this real quick, -6 on top, 5 on the bottom, what's going to multiply to a -6 but add a +5? Well, it'd be a +6 and a -1. And so I'm going to get x plus 6, because when we deal with it in the factored form, we're going to put our signs as we have them, and x minus 1, because when we multiply this back out, 6 times -1 is the -6, and 6x minus 1x would give us the +5x. And so setting each of these equal to 0, we get x is equal to -6 and x is equal to +1. And so my two intercepts are going to be at +1 and -6. And if we think about how far away these are, this is 2.5, 3.5 to the right, and this is 2, 3.5 to the left. And so my graph would continue up through those points on both sides, right? Now, think about where this shading would be. X, all this is less than the y value, right? So if I plug in 0 and 0, and there's already a 0 in for the y, so is the order pair 0, 0 going to fit? Well, is -6 less than 0? Yes. And so that means that my point is in here, right? Which means my shading for this would be inside this parabola, right? So all this would be shaded in. But the only part I care about, again, go back to what we talked about, right? We're only dealing with one variable. We're only talking about the x values here. And so when we solve this, I only care about where this shading would be on the x-axis. Well, at -6 and at +1, it's a dashed line. So am I equal to? No. So what really would be here are a pair of circles. And where's my shading? Well, my shading is in between. And so the solution to this problem is that it's going to be from -6 less than or equal to x, not less than or equal to, because it's not equal to, right? Be less than x and less than +1. Or we could say it's on the interval from, not with brackets because it's not equal to, -6, +1. So does that make sense there? As we look at this problem again, we're looking at where our shadings are, what we're doing at our endpoints, right? And so that is one method of solving this. And I want to show you a second method, because while we can do everything going to the coordinate plane and solving it all out, we can just go back and solve this algebraically as well. And so let's look at example B. Negative 4x squared plus 5x plus 7 is greater than or equal to 0. And so if we can factor this out, which we're going to try first, let's see what happens. Because again, if we go back here, right, I had to factor it anyways to figure out where it crossed the x-axis. And so doing this one here, we're going to get negative 28 and we're going to get 5. So what are two things that are going to multiply to negative 28 and add to 5? Well, what multiplies to negative 28? Well, you would get 1 and 28, you would get 2 and 14, and you get 4 and 7. So none of those add to 5. So does it factor? No. And so we have to use some other methods here. We could use the quadratic formula. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So x is equal to the opposite of 5 plus or minus the square root of 5 squared minus 4 times negative 4 times 7 all over 2 times the negative 4. And so x is equal to the opposite of 5 plus or minus the square root of 25. 4 times 4 is 16, and 16 times the 7 is going to give us 112. And so this is all over negative 8. And so we're going to get that x is equal to negative 5 plus or minus the square root. 25 and 112 is going to give us 137 over the negative 8. And the square root of 137, when we go to our calculator, square root of 137 is 11.705. So negative 5 plus or minus, this, not the square root anymore because we've taken the square root, of 11.705 with rounding over the negative 8. Now, at this point, we're going to change this equal sign to an approximately equal to sign because we've rounded at this point. And then to find our answer, so we're going to do negative 5 plus the 1107 or 11.705, and then we'll divide that by the 8, and then we'll do the subtraction. And so on the plus side, negative 5 plus the 11.705 is going to give us 6.705, and we'll divide that by the negative 8. Our other will give us negative 5 minus the 11.705, and so that's negative 16.705 divided by the negative 8. And so dividing, we'll do the bottom one first. So dividing this, again, these are approximately equal to at this point, and so approximately equal to 2.088. And then for our top one, the 6.705 divided by negative 8 is negative 0.838. And so what we end up with, thinking about our number line here, zero's in the middle here, we're going to have this value, which is negative 0.838, which equates to, if we talk about this value here, the negative 5 plus the square root of 137 over the negative 8. And we can deal with the negatives here and simplify this a little bit, but we're just going to leave it as is. And then the other side is the 2.088. And again, that equates to the negative 5 minus the square root of 137 over the negative 8. And so go back to our original problem. We're greater than or equal to, so I'm going to put dots at both of these points, right? And then the question becomes, is 0 a solution or not? Well, if I plug in 0 for x, 0, 0, and 7, right? So I got 7 is greater than 0. That is true. So my shading for this one would be in between. Because again, 7 is greater than 0, and I plugged in 0 for x. It came out true, not false. Had it come out false, then my shading would end up going to the left and to the right because I could test like negative 1 or negative 2, and those points would work. And I could test 3 or 4 or 5, and those points would work as well. Again, test your points. If we go back to the steps at the start, remember the last thing was to test some points to know where your shading is going to go. Okay, so again, this one's a little more convoluted because we had the quadratic formula in there. It didn't factor nicely, but again, if it factors nicely, it's a little bit easier of a problem, but the quadratic formula is still going to give you those solutions that you need. Last thing we're going to look at, and this is dealing with that second standard we talked about dealing with application here, The height of a ball above the ground after it's thrown upward at 40 feet per second can be modeled by the function h of t is equal to 40t minus 16t squared, where h of t is the height given in feet and time t is in seconds. At what time of its flight is the ball within 15 feet of the ground? So let's draw a picture real quick and see what we're talking about, right? So we've got somebody standing here about to throw a ball, right? Now, based on this function here, right, we're throwing it from exactly on the ground. We're not talking about being up here. We're actually talking about being on the ground, so maybe like kicking it, right? It says it's thrown, but it doesn't make sense to throw it from the perfect ground. But again, it's not a perfect example. And so again, this ball is being thrown up. Well, it says, at what time of the flight is the ball within 15 feet of the ground? So if we're talking about our height, right, our height above the ground, here's 15 feet. I'm looking for at what time, right, not distance, what time is this ball beneath this line? It says within 15 feet of the ground. Now, the term within would include the 15. So this is going to be less than or equal to, right? So we're going to have that our height of time is equal to 40t minus 16t squared. So the height that is my critical value is the 15. And I want the 15 to be larger than or equal to what my height is for this function. And so now we can begin to solve it. And again, we could use different methods here, but let's try and just simplify this first. I can divide everything by the 5, or no, I can't divide by 5 because that's a 16 over there. And so let's try and move this to the other side. Or we could try to make this a perfect square trinomial. But again, some of our values here are not great to do that with. And so let's see if we can factor it first. So minus the 15 and minus the 15. So 0 is greater than or equal to, and I'm going to reorder some things here, negative 16t squared plus the 40t minus the 15. I could divide by the two negatives and get this to flip around. But here's what's going to happen if I divide by these -1, right? But if I divide by -1, means I also have to flip this inequality. So don't forget about that, right? Those rules don't go away just because I'm dealing with a new type of problem, right? And so let's see if I can factor this, right? 16 times 15, that's 225 plus another 15, so that's 240, and I got -40 here. When we go through all our pairs of 240 and trying to get -40, we get close because you got 24 times the 10, that would give you 34, and we've got 8 times 30, so 30, and so we get 38, but there's nothing that gives us 40 exactly, and again, the signs would be the same because we're multiplying to a positive, adding to a negative here. And so we'll go to the graph and graph this up. And so we're going to graph this function right here, and then we're also going to put a line across like we did up here at that 15. And so I'm going to bring that image in now. And so as we look at this graph, we're going to see that I've graphed two things here. The first is the parabola itself, so that's the h of t is equal to 40t minus 16t squared. That's the parabola we're seeing here. And then I've also graphed h being less than or equal to 15. That's the blue shaded region here. And so we're looking for what times is this graph there. And so I've got an intersection here and an intersection here. This is at 0.459, comma 15. And this point is at 2.041, comma the 15. And so where is this shading? Obviously, so it's from 0 time until we get to this, and then it's from 2.01 until our graph ends, and it takes it at the ground at 2.5 seconds, comma 0. And so we have some restrictions here as well because, again, our ball's not going to go under the ground. And so we end up with two intervals here, and so we're going to be, where's this ball from start to finish? So from 0 to 0.459, again, the endpoint is included here, union 2.041 to 2.5, or we could say t less than or equal to 0.459, or t greater than or equal to 2.041. But again, we've also got to understand that our domain, right, our domain is only from 0 to 2.5 on this, right? So this affects this, right? Because again, t can't be less than 0 because it's not in our domain. T can't be greater than 2.5 because again, it's not in our domain. So that's what we're looking at here. Again, I know this is kind of a convoluted example a little bit, but the key is understanding that we can go to our graph, right? Because remember this other standard we talked about, right? Complicated examples through technology, and our solutions here don't come out very nice. And so we're going to use technology some to help us through these today. But make sure you do show your work as you're doing it. The word of the day is inequality. And so I hope y'all have a great day. The review will be tomorrow and the test will be on Thursday this week, which means again, we have enrichment on Thursday to prepare a little bit before fourth block. So again, hope y'all have a great day. And don't forget, if you got questions, you know what you got to do. Ask. Y'all have a good one. Bye.